Hello everyone and welcome to our today's class. It is our first lesson on the topic magnetic effect of an electric current. So as usual, let me commence by giving you the quote of the day, which states that life is like riding a bicycle, such that for you to stay balanced, you must keep moving. So we'll discuss that quote at the end of our class today. So today we are looking at magnetic effect of an electric current, but we have a professor of physics who was called Hans Osten. Actually is the professor who discovered magnetic effect of an electric current. So he did discover that actually a conductor carrying current has a magnetic field around it. Although we had various scientists who contributed to that discovery. For example, we have a scientist called Michael Faraday who actually came up with the Faraday's law. We'll look at the Faraday's law in a certain topic in Form 4 called electromagnetic induction. So to demonstrate his discovery, he carried out an experiment. So this is the experiment that was carried out by Hans Osten, that is in the year 1820. So the experiment is to investigate the magnetic effect of a current flowing through a conductor. So the apparatus required are one, direct current power source. This is our direct current power source. Then we also need connecting wires. These are our connecting wires. Then of course we also need a switch. This is our switch. Then a rheostat, or sometimes we call it a variable resistor. Then we also have two magnetic compasses. So you have this, our first magnetic compass, then our second magnetic compass. Then of course you also need an ammeter for recording the amount of current flowing through the circuit. So the procedure that he followed was, one, you set up the apparatus as shown in this diagram. Then you hold the wire over but in line with the compass needle A. So you take the wire, this wire should pass, hold the wire over but in line with the compass needle A, and in line but below compass needle B. So you pass this wire in such a way that it is passing over or above compass needle A, then such that it is passing below the compass needle B. Then after that, you close the switch, that is you close this particular switch and observe the compass needles. Then you vary the strength of the current using, of course, the rheostat or the variable resistor, and note the effect of the needle, that is, observe the deflection of the needle. Then after that, you repeat the experiment with the battery polarities reversed. You now reverse the positive terminal, you reverse the connection of the positive terminal and the negative terminal. Remember, whenever you reverse the polarities of the battery, that means the direction of current of flow will also be reversed. Now, to predict the direction in which the needle A and B, or the compass needles A and B, will deflect, he needed what we call the Ampere's swimming rule. So the Ampere's swimming rule states that if one imagines one is swimming along a wire in the direction of the current and facing the compass needle, then the north pole of the needle will be deflected towards the swimmer's left hand. That if you imagine that you're actually swimming along the direction of the current, so if this is the positive terminal, then it means the current will always flow in this direction. Remember, the larger bar always represents the positive terminal, while the smaller bar represents the negative terminal of the battery or of the cell. Now, if this is the larger bar, then it means the current is flowing in this particular direction. So the Ampere's swimming rule is requiring us to imagine that a person is swimming along this in the direction of the current and along this wire. Then that if such a person is moving in the direction of the current, that is, and facing the compass needle, then the north pole of the needle will be deflected towards the swimmer's left hand. Now imagine you are the person swimming along this wire in this direction of the current. Then when you reach here, automatically your right hand will be on the lower side, while the left hand will be on the upper side. So the Ampere's swimming rule predicts that this particular needle will deflect on the side of your left hand, or of the left hand of the swimmer. Therefore, I expect needle A to deflect upwards. Remember, for needle A, the wire was passing above it. But if you connect it in such a way that the wire is passing below now the needle B, now the direction of deflection of the needle actually reverses. So if this one deflected upwards, then automatically for B, the needle would deflect downwards. Now, he also tried the experiment after reversing the polarities. That is, if we connected these cables or the battery in such a way that the positive terminal becomes on this other side, then the negative terminal on the other side, then if the positive terminal was here, it means the current will now be flowing in this particular direction. So if you imagine that you are the swimmer, if you are swimming in this particular direction, that is along the direction of the current, then when you reach here, actually your right hand will be upwards and your left hand will be downwards. Then also for this case, your right hand will be on the upper side and the left hand will be downwards. So he predicted that the deflection of this particular needle will be downwards according to this experiment. That is, the deflection of the needle should always be towards the left hand side of the swimmer. So needle A will deflect downwards if the polarities of the battery are reversed, or if the current was moving from this particular terminal. If the current was moving this way, then needle A, remember needle A, the wire was passing above it. The wire was passing above needle A. So the left hand will be downwards. That is, if you are swimming towards this direction, then the right hand will be upward. So I expect needle A to deflect downwards. Then of course needle B will deflect in the opposite direction. Automatically needle B will deflect upwards. Needle B will deflect upward. So once again, we said that the Ampere swimming rule states that if one imagines one is swimming along a wire in the direction of the current and facing the compass needle, then the north pole of the needle will be deflected towards the swimmer's left hand. Next, we look at what we call the Maxwell's screw rule. We look at what we call the Maxwell's screw rule. So of course, screw rule, because the experiment itself is involving a screw. So the Maxwell screw rule states that if a right-handed screw is driven forward in the direction of the convectional current, then the direction of rotation of the screw is the direction of the field lines. Now imagine that this is your screw, then you want to drive it forward. That is rotation of the screw. That is, you are rotating it in the direction shown by this particular arrow here. So if you are rotating the screw, or you are driving the screw forward such that it is moving downwards, then the direction of the rotation of the screw will be similar to the direction of the field lines. That is what simply the Maxwell screw rule is stating, that if we are rotating this screw in this particular direction, then we also expect the magnetic field lines to be moving in a similar direction to that of the rotation of the screw. So the Maxwell's screw rule states that if a right-handed screw is driven forward in the direction of the convectional current, then the direction of rotation of the screw is the direction of the field line. So if we are rotating the screw in this direction, then also the field lines will be rotating in a similar direction to the direction of rotation of the screw. So if we were rotating it maybe in this other direction, then we will expect the field lines to move in the opposite direction. But the most important thing here to note is that the direction of the rotation, of the forward rotation of the screw line, is also the direction of the rotation or the direction of motion of the field line. So once again, we've said that the Maxwell screw rule states that if a right-handed screw is driven forward in the direction of the convectional current, then the direction of rotation of the screw is the direction of the rotation of the field line. So if the screw is rotating in this direction, this is the clockwise direction, then I also expect the field lines to rotate in the clockwise direction. So this is the direction of motion of the current. So the current is downwards. This is a straight wire. Then direction of the magnetic field. Then next we look at what we call the Fleming's right hand grip rule for a straight conductor carrying current. The Fleming's right hand grip rule for a conductor, for a straight conductor carrying current. Now, the Fleming's right hand grip rule for a conductor, for a straight conductor carrying current, states that if a conductor carrying current is grasped in the right hand with the thumb pointing along the wire in the direction of the convectional current, comma, the fingers will point in the direction of the magnetic field. So that is what the right hand grip rule actually for a straight conductor carrying current states. That if a conductor carrying current is grasped in the right hand with the thumb pointing along the wire in the direction of the convectional current, the fingers will point in the direction of the magnetic field. Now, the first thing to note when you are using a right hand grip rule is that you should always use your right hand when you are grasping your conductor. So assuming this is my conductor, then assuming the direction is flowing in this, the current is flowing in the forward direction, that is as indicated by this particular arrow, then the right hand grip rule is instructing us that if a conductor carrying current is grasped, that is, to grasp is to hold it. As you can see, the right hand is holding this particular conductor, of course, with the current. That if a conductor carrying current is grasped in the right hand with the thumb, remember this is the thumb, with the thumb pointing along the wire in the direction of the convectional current. So if this is my direction of the current, then I will point my thumb in the direction of the current. Then the right hand grip rule predicts that the fingers will point in the direction of magnetic field. So if my thumb is pointing along the direction of the current, then this is my right hand. Then as you can see, my fingers are pointing in this direction. So the direction of curling of my fingers here represent the direction of the magnetic field. So in this case, the magnetic field will be moving in this direction. They will be moving in this particular direction. That is along the direction of my fingers here. So the curling, the direction of curling of the fingers represents the direction of magnetic field. So once more, we've said that the Fleming's right hand grip rule for a straight conductor carrying current states that if a conductor carrying current is grasped in the right hand with the thumb pointing along the wire, in the direction of the convectional current, comma, the fingers will point in the direction of the magnetic field. Then you also remember it must be the right hand, because if you try it the same rule but using the left hand, the direction will actually be opposite. So you have to be careful. You must use the right hand. Now we can also demonstrate the same, now indicating the direction of the magnetic, or the direction of the magnetic field, or the direction of the magnetic field lines. Remember, the direction of the magnetic field will be same as the direction of magnetic field lines, because the magnetic field lines or the lines of force are the ones that form the magnetic field. So the direction of the magnetic field line is automatically the direction of the magnetic field. So if I apply the same rule, that if this is my right hand, actually try with your right hand, you realize that actually the rule does work. Just imagine you have a conductor, for example, you can just hold a nail, then assume that the direction of current of the current flowing through that particular nail is upward. Then you align your thumb. Remember, the thumb is the larger finger, or the finger that is broader than the other fingers. So this is my thumb. So if I grasp or if I hold this conductor of mine such that my thumb is pointing along the direction of the current, then the fingers, you can see how the fingers are curling, or how they are grasping, or how they are curling my conductor. Then that the fingers, the direction of curling of the fingers is the direction of the magnetic field. So as you can see, my fingers are curling in this particular direction. Actually, this, if I had a clock here, I think this would be the, is it clockwise or anti-clockwise? I think this would be an anti-clockwise direction. But the direction of curling of the fingers is the same as the direction of the magnetic field or the magnetic field line. So that is simply what the right hand grip rule states. So as a student, you should be keen to know how to apply the right hand grip rule. We also have the left hand grip rule, which we will look at later on. But the most important thing to remember is that when you are using the right hand grip rule, always remember to use the right hand. You use your right hand and not the left hand. So once more, we've said that the right hand grip rule for a straight conductor carrying current states that if a conductor carrying current is grasped in the right hand with the thumb pointing along the wire in the direction of the convectional current, the fingers will point in the direction of the magnetic field. So you just align your thumb along the direction of the current in a conductor, then the curling or the grasping of your fingers, the direction of the other fingers apart from the thumb, simply represent the direction of the magnetic field. So as you can see, the fingers are curling in this direction. Also, the direction of magnetic field is also this way. That is as indicated by the arrow. So the direction of magnetic field should be similar to the direction of curling of my fingers. Then next we look at the right hand grip rule, but for a loop carrying a current. The right hand grip rule, but for a loop carrying a current. So a loop is just a circular, just many magnetic field, but maybe in a circular, or you assume you have grasped them. They are like in originating from the same point, of course, but they are like in a loop or a circular manner. Now, the right hand grip rule for a loop carrying a current states that if the fingers of the right hand encircle the current loop such that they point in the direction of current, the thumb points in the direction of the magnetic field formed through the inside of the loop, So actually, the right hand grip rule is almost the same like for the straight conductor, only that we are now using a loop carrying a current. So that if you just assume you are grasping actually these magnetic field lines, then of course your thumb has to point in the direction of the current. Like for this case, this is current in, then this is current out. So automatically this means that the current is moving in this particular direction. That is, it is entering through this end of the loop, then it is moving in this direction, then actually it comes out through this particular direction. Then the right hand grip rule for a loop carrying a current so states that if the fingers of the right hand, now assuming this is my right hand, actually it is my right hand, if the fingers, these are the fingers and this is the thumb, if the fingers of the right hand encircle the current loop, so the current is actually moving in this direction, but it is somehow circular. So you take your fingers to encircle. To encircle is like to take in a circular path. As you can see, the current is actually moving in a circular path. So you place your fingers in such a way that they are aligning with the direction of the current, because the current is entering through here and leaving through the other end. So if the current are entering through this direction, I also curl or make my fingers in such a way that they are encircling the current loop. That if the fingers of the right hand encircle the current loop such that they point in the direction of the current. Now remember, this is the direction of the current. This is current in, then this is current out. So the current is moving in this direction. I also make my fingers in such a way that they are curling or encircling and curling towards the direction of the current. That if the fingers of the right hand encircle the current loop such that they point in the direction of the current, then the thumb points in the direction of the magnetic field formed through the inside of the loop. Now, as you can see, when I'm encircling this particular loop in the direction of the current, actually my thumb is pointing upwards. No, my thumb is pointing in this direction. That is out of the paper. The thumb is pointing in this direction. So the direction of pointing of the thumb would represent the direction of motion of the what? Magnetic field, or the magnetic field line. That's why you are seeing me indicating the arrow or the direction of the magnetic field lines to be actually in alignment with the direction of the thumb. So once more, we've said that the right hand grip rule for a loop carrying a current states that if the fingers of the right hand encircle the current loop such that they point in the direction of the current, comma, the thumb points in the direction of the magnetic field formed through the inside of the loop, Now we can also apply the same principle, but now for different we look at magnetic field patterns around current carrying conductors. Now whenever you see this symbol, it actually means that the current is moving downwards. That is, the current is moving inside the paper. So we assume the current is moving downwards. If it was in 3 dimensions, I will be able to show you clearly. But it simply means that whenever you see an X, it means the direction is moving downwards or into the paper, that is downwards into my paper here, into the paper. Now if the direction is moving downwards, now you just take the same right hander, then you place your thumb in such a way that the thumb could be moving. Now remember, here we want to determine the direction of motion of the field line. So we simply align the thumb along the direction of the current. Now because the current is into the paper, it means we will take our thumb, then we point the thumb downwards or into the paper. Now try it practically. If you place your thumb, I'm also trying, if you place the thumb of your right hand in such a way that the thumb is pointing downwards, you realize that the fingers are curling in this particular direction. The fingers, actually my fingers are also curling in this particular direction. That is, they are moving towards that direction. So try it practically. Just place your thumb downwards or into the paper, then observe the direction of the curling of your fingers. So the direction of the curling of my fingers is actually this direction. So the fingers curl towards this direction. So the direction of the curling of the fingers represents the direction of the magnetic field. That is, we are just reversing the law upward here, the right hand grip rule. So if you are given the direction of the current, you place your thumb towards the direction of the current, then identify the field. But if you are given the field, then they want you to identify the direction of the magnetic field. You just place your fingers towards the direction of the current, you curl them towards the direction of your current, then the thumb will always point in the direction of the magnetic field. And remember, the magnetic field always originates from the North Pole. They originate from the the magnetic field lines, yes, they originate from the North Pole and end at the South Pole. So if we were imagining to name maybe the polarities of the magnet, then automatically the North Pole will be towards this direction, then the South Pole will be towards the other direction. Because magnetic field lines will always originate from the North Pole towards the South Pole, as we saw in a topic called magnetism. Maybe if you can't trace it clearly, you can just review our first lesson on the topic magnetism. Then actually you will see that the field lines, you look at the properties of the field line, that is how they move and also how they do behave. If I apply the same here, now whenever you see a dot, this one means that the current is moving upwards or out of the paper, So in physics, if we want to represent that the current is moving out of the paper, we represent it with a dot. But if we want to represent that the current is moving down the paper, that is downwards, we represent it with a cross. So whenever you see a cross in physics, it simply means the current is moving into the paper or downwards. But whenever you see a dot, that should imply that the current is moving what? upwards or outside the paper. Now for this case, if the current is moving upward or outside the paper, then it means we will have to align our thumb to be pointing upwards. Now remember, it is strictly the thumb of the right hand. If you try the thumb of the left hand, you will get opposite results. So you take the thumb of your right hand, then you position it upward. You just position it upward, then observe the direction of curling of your fingers. That is the first finger, the second, the third, and of course the fourth finger. So if you place your thumb pointing upwards, you realize that your finger are actually curling in this particular direction. I'm trying it practically here and it's working for me. Also try it practically and see whether actually when your thumb is pointing upwards, your fingers are curling in this particular direction. Then of course drop a comment if yours is working like mine. Then for this case, this is current moving downwards. So remember, we said that a cross represents current moving downwards. So for this case, you will take your thumb pointing downwards. So if I point my thumb downwards of the right hand, actually my fingers are curling in this particular direction. So the direction of curling of the finger represents the direction of magnetic field lines. So also the same case here. Here the current is moving downwards. If I place my thumb pointing downwards, actually my fingers are curling in this direction. So this represents the direction of the field lines. Same case here. If my finger is pointing, if my thumb is pointing downwards, then my fingers, that is, you just take this thumb, then you point it downwards or into the paper, then observe the direction of in which these fingers are curling. You realize that if I place my thumb here with the fingers, with my thumb pointing downwards, that is, downwards means towards the direction of the current, then actually I realize that my fingers are curling in this direction. So this direction represents the direction of the magnetic field. Also remember here, because we have attractive forces, which means then this is a neutral point. Then here we have repulsive forces. Remember, repulsion only takes place when there are two like poles together. So that is to mean, if you were to predict maybe the polarities, maybe if this was a north pole, this would also be a north pole, so that they are repelling each other. But if for this case, if one is a north pole, then the other one is a south pole, that's why there is attraction between those particular two. Even you can see it from here. Actually here the fields are moving in this direction, but here the fields are moving in opposite direction, meaning the polarity here, if I was to place my polarities here, this will be, there will be a north pole here, because the magnetic field lines move from the north pole, then a south pole here, then here automatically there will be a south pole here and here a north pole, because the magnetic field lines move from the north pole towards the south pole. Now remember, since we could be having a north pole here, then a south pole here, remember, a north pole and a south pole will always attract each other. Also here, if field lines are moving in this direction, it means this one represents a north pole, then field lines are moving towards, that is, they are entering towards this region, then this will represent a south pole. Then a north pole and a south pole will always attract each other. That's why we have attractive forces here. Contrary, here the direction is moving upwards, also the direction of field lines is moving upwards, meaning the north pole is downward here, then the south pole is upward here. So this is a north pole, then there will also be a north pole down here. Now north pole and north pole will always repel each other, because from the law of magnetism we did say that like poles repel, and like poles attract each other. So because of the repulsion, that's why we are talking of what? Repelling forces or repulsive forces. Next, we look at an electromagnet. Now, what is an electromagnet? So an electromagnet is actually a temporary magnet made by passing a direct current through a soft iron core. So that is an electromagnet. So if you are asked to define an electromagnet, you simply say that an electromagnet is a temporary magnet made by passing a direct current through soft iron core. Remember, direct current is denoted by DC. So whenever you pass a direct current through a magnetic material, and especially the soft ion core, because soft ion core can easily be magnetized and demagnetized. So because we want a material which can be magnetized faster, that's why we are using a soft ion core. So you simply pass a direct current in a soft ion core, then you will obtain your electromagnet. Then we are saying that an electromagnet is a temporary magnet. Temporary because soft ion core can easily lose its magnetism. That is, it can easily be magnetized and demagnetized. So the level of the magnetism is actually temporary. It is temporary. So an electromagnet is a temporary magnet made by passing a direct current through a soft ion core, or simply a soft magnetic material. So we use soft ion ore is used because it is easily magnetized and easily demagnetized. Alternatively, you can just say we prefer using soft ion core and making an electromagnet because it is a soft magnetic material. So from magnetism, we did say that a soft magnetic material are those that are easily magnetized and demagnetized. Also, the soft ion core actually concentrates the magnetic field lines or the magnetic fields within the coil. So you can be asked to give two reasons why we prefer using soft ion ore when making electromagnet. So the first reason is because soft ion core or ore is a soft magnetic material, or you can say we prefer using soft ion ore because it can easily be magnetized and demagnetized. But our main point here is the magnetization. It is easily magnetized. Then we are also saying the other reason is because the soft ion core or ore concentrates the magnetic lines of force or the magnetic field within the coil. So remember, when the magnetic field lines are concentrated, it means the magnetic field is actually stronger. It will be stronger. Then whenever we want to predict the north pole of the electromagnet, we can easily use what we call the right hand grip rule. So the right hand grip rule can be used to predict the north pole of an electromagnet. So we use the right hand grip rule to predict the north pole of an electromagnet, as we will see in our next experiment. So we conduct an experiment that can be used to show us how we make an electromagnet. So this is an experiment to investigate how the size of current flowing in the solenoid affects the strength of an electromagnet. So in this experiment, the apparatus required are: one, we need a long insulated copper wire, Then we also need a rheostat. This is our rheostat, or the variable resistor. We also need a power source. We need our power source here, like you have our battery here. Then we also need so our power source can be a lead acid accumulator, preferably maybe of 6 volts. Then of course we also need a switch, that is for opening and closing the circuit. Then we also need a dish containing paper pins. So this is our dish, then it is containing the steel pins. Then of course we also need an iron rod. So this is our iron core, or what we are calling the iron rod. Then after that, the procedure that we will use to set up or to carry out the experiment is that: one, you wind around 20 turns of insulated copper wire tightly around the iron rod. So this is what we are calling our copper wire. Of course it is insulated. So you insulate it, meaning it's actually a cable, or it has some insulator or plastic material which is covering it. So you wind around 20 turns of insulated copper wire tightly around the iron rod. So this is our iron rod. You simply encircle, or you wind our copper wire around our soft iron core. Then after that, connect it to the battery as shown here. So after winding it, of course we connect it to the battery. This is our battery here. After that, you switch on the current and adjust the variable resistor or the rheostat to give a current of maybe around 0.5. So after connecting, we close the switch, then we vary our rheostat. Remember, the rheostat will determine the amount of current passing through the circuit. So maybe we set a small current of maybe around 0.5 amperes. Then we look at the observation. We observe what happens to the steel pins. Then we also repeat the same experiment, but increasing the amount of current. Of course, the rheostat will help us to increase the amount of current. Maybe we increase it to 1.5 amperes, maybe next to 2 amperes, maybe next to 2.5 amperes. Then we observe what happens to the steel pins. Now, in this particular experiment, it is observed that actually as you increase the current, the steel pins get attracted to this particular iron core. The steel pins get attracted to this particular iron core, showing that actually the iron core is magnetized. Remember, we did look at how to magnetize a magnetic material by electrical method. It is actually the same process or the same procedure. So you remember that we also have to use a direct current or a DC current. When you close the circuit, then you adjust the current maybe to 0.5 amperes. It is observed that the steel pins, some of the steel pins will actually be attracted to the soft iron core. So maybe assuming when the current is 0.5, maybe 2 pins get attracted. When the current is increased maybe to 1.5, maybe 5 pins will get attracted or will get hooked here. Then if we increase the current to a maximum value, maybe 2.5 or even 3 amperes, it is observed that more steel pins will be attracted to the magnet, actually showing that the strength, the more the current supplied, the more the level of the magnetization of the soft iron core, therefore the more the attraction of the steel pins. So as the current is increased, the mass of the pins supported, that is representing the strength of the magnet. As the current is increased, more pins will get attracted to the soft iron core. Why? Because whenever a direct current is passed through a solenoid, which is wound on a soft iron core, actually the soft iron core gets magnetized, or it acquires magnetism. When it acquires magnetism, it means now it has the ability to attract any magnetic material. So it has the ability to attract steel pins, which are actually magnetic material. Now remember, in this experiment we are using steel pins strictly because steel pins, we categorized steel under the hard magnetic material. That is, they take a lot of time to be magnetized, but once they are magnetized, they retain their magnetism. So if you take a steel pin, once it is held here, it actually retains the magnetism for some time. So it clings here for some time. But of course, whenever you open the circuit, the current disconnects, then after sometimes the steel pins will actually fall off. So as the current is increased, the mass of the pins supported into bracket, that is representing the strength of the magnet, increases. So beyond a particular value, however, the strength of the electromagnet remains what? Constant. So you can supply the current up to a maximum value. So the magnetism of the soft iron core gets to a maximum value. Remember, in the domains theory, what we used to call the magnetic saturation. So it reaches at a point whereby even if you continue increasing the current, actually the magnetism will not increase, because such a material has reached what we call magnetic saturation. So as the current is increased, it is observed that the mass of the pins supported, which are representing the strength of the magnet, also increases. So as the current increases, more pins get clinked here or attached here, because as the current is increasing, the soft iron core is becoming more magnetized. Remember, if we were to plot a current, a graph of maybe the strength of the magnet and the amount of current, then the strength of the magnet will be directly proportional to the amount of current, meaning we will obtain a straight line graph through the origin. So of course, representing the direct proportionality. So as the strength of the current increases, also the strength of the magnet increases. But that graph will reach at a point where it flattens. That is where the soft iron core has reached what we call magnetic saturation. So remember, if a material reaches at magnetic saturation, even if you continue supplying the current will not increase the magnetism. The current won't increase the magnetism because all the dipoles have fully aligned. So next, we look at the factors affecting the strength of an electromagnet. What are the factors affecting the strength of an electromagnet? So the first factor affecting the strength of an electromagnet is the number of turns of the coil. That is, this is my coil. The number of turns of these particular coils affects the strength of the electromagnet. That is, determines how strong the electromagnet will actually be magnetized. So of course, the more the number of turns of coil, the stronger the electromagnet. So if you want your electromagnet to be stronger, you actually use more turns. So that means you use a larger or a longer copper wire, then you wind it. You make as many turns as possible, because the more the number of turns, the more the strength of the electromagnet. So the first factor affecting strength of an electromagnet is the number of turns of the coil. The number of turns of the coil. Then you are saying that the strength of an electromagnet is directly proportional to the number of turns of coil. That is to mean, the more the coils, the stronger the electromagnet. The fewer the number of turns of the coil, the fewer the strength of the electromagnet. The second factor affecting the strength of the electromagnet is simply what we call the current flowing in the coils. That is the amount of current flowing through the coils. So as we saw, actually, the more the current, the more the steel pins will be attached. Meaning, the more the current, the more the strength of the electromagnet, the more the attraction of the pins. So the current flowing in the coils is our second factor affecting the strength of the electromagnet. So of course, the higher the current flowing through the coils, the stronger the electromagnet. So we are also saying that the amount of current flowing through the coil is directly proportional to the strength of the electromagnet. So the more the current, the stronger the electromagnet, or the more the strength of the electromagnet. The lesser the current, the lesser the strength of the electromagnet. The third factor is the shape of the core. Like for this case, we are using a straight core. Sometimes we also have what we call a U-shaped or a circular core. Now, whenever we use a circular core, the strength of the electromagnet will be more than when you use a straight core. So we look at the reasons behind that. So the third factor, we are saying that the shape of the core. Then under that, we are saying that a U-shaped core makes stronger electromagnet than a straight core. Like you remember the same reason when we are looking at the horseshoe magnet. We did say that the horseshoe magnet will always have stronger magnetic fields than the straight magnet. And the reason is because a U-shaped core brings the poles closer together, hence the lines of force get more concentrated. They get more concentrated. Remember, a horseshoe or a U-shaped magnet means it will be like in this shape. That is the U-shaped. But we adjust this one to be closer to the other one. So a U-shaped magnet actually brings the polarities together. That is, the north pole and the south pole becomes closer to each other. And closer they are, it means the stronger the magnetic fields, because they are concentrated together. So if you are asked to give a reason why a U-shaped core makes a stronger electromagnet than a straight core, the reason is because a U-shaped core brings the poles closer together, and hence the lines of force get concentrated. But a straight core, actually, you can see the north pole is down here and the south pole is up there. The farther the poles are, the weaker the strength of the electromagnet, or the weaker the magnetic field. But the closer the poles, the stronger the magnetic field. Now, we also did say that we can determine the direction of the electromagnet, of course, using the right hand grip rule. Like for this case, I have my current. The current is flowing in this particular direction. The current, we did say that the larger bar represents the positive terminal. So the current is flowing in this particular direction. The current is flowing this way, this way. Then it gets out up to the negative terminal. So remember, if you are using the right hand grip rule, you simply curl your fingers in the direction of the current of the core. So if the current is coming from the positive terminal, then the current is moving actually this way. Remember, this one is passing upwards, but on the other side it's passing downwards. So if this one is passing upwards, you also align your fingers of the right hand in the direction of curling of this particular coil, or what we are calling a solenoid. So if I curl my fingers, the fingers of my right hand, you also try curling your fingers in this particular direction. That is, your fingers should be pointing from upwards downwards. They should be pointing downwards in the direction of the curling of the coil. Then you realize actually your thumb will be pointing downwards. So the thumb is pointing downwards. So remember, the downwards, the thumb always points in the direction of the North Pole. The thumb will always point in the direction of the North Pole. That's why you are saying that this is a North Pole and this is a South Pole. Remember, in an exam situation, they don't tell you that you use the right hand grip rule. They just give you the apparatus, then they ask you to state the direction of, maybe they can name this one X and this one Y. Then they tell you to indicate or to set the direction of X and the polarity of X and the polarity of Y. So here we use the right hand grip rule. You just take your fingers, then you curl them towards the direction of the current. Then of course the direction in which the thumb will point will be the direction of the North Pole. Now, if the polarities were reversed, assuming this was the positive terminal and this would be the negative terminal, then it means the current will be moving in this direction. So if the current was moving in this direction, it means when you are curling your finger, you put your fingers downwards, then they emerge from the other side. Now, if the fingers are curling, you take your fingers through downwards, then they emerge upwards. If your fingers are curling downwards, then emerging from upwards, you realize that your thumb will be pointing upwards. So the upper direction will be the North Pole, then the lower direction will be the South Pole. But based on the diagram, according to the direction of the current here, the North Pole will be downwards, because if I curl my finger of the right hand, the thumb points downwards, and therefore the North Pole becomes the down direction. Then the fourth and last factor affecting the strength of an electromagnet is the length of the solenoid. Then here we are saying that the longer the solenoid, the weaker the electromagnet. That the longer the solenoid, the weaker the electromagnet. So the solenoid is just the curling. If you take a wire and curl it such that it is maybe somehow like in a circular shape, then that is what we are calling a solenoid. So like this one here is actually our solenoid. So the length of the solenoid, that is the distance from where the solenoid is ending or where the curling of the wire is ending, this distance from here up to down here, or the distance from here up to upper here, that the longer this distance is, the weaker the strength of the electromagnet. So remember, if you want your electromagnet to be stronger, you bring this the curling of this particular wire, the copper wire, you bring them close together. If they are closer together, it means the length of the solenoid is actually shorter. So the shorter the length of the solenoid, the stronger the magnetic field, or the stronger the electromagnet. But if the length of the solenoid, that is the distance of the curling, that is the distance from here of this particular wire up to here, the longer that distance is, the weaker the strength of the magnet. Then the shorter that particular length of the solenoid is, actually the stronger the electromagnet. So we have said, in summary, we have said that the four factors affecting the strength of the electromagnet are: 1, the number of turns of coil. The explanation is that the more the number of turns of the coil, the stronger the electromagnet. Then 2, we have talked of the current, the amount of current flowing in the coils. Then we have said that under that, the higher the current flowing through the coils, the stronger the electromagnet. The third factor was shape of the core. Then we've said that a U-shaped core makes stronger electromagnet than a straight core. Then the reason we have given is because a U-shaped core brings the poles closer together, hence the lines of force get concentrated. Then the last factor was then the length of the solenoid, then we have said that the longer the solenoid, actually the weaker the electromagnet, the weaker the electromagnet. Then lastly, we look at what we call force on a current carrying conductor in a magnetic field. The force on a current carrying conductor in a magnetic field. To predict that force, we use what we call the Fleming's left-hand rule, also called the motor rule. So the motor rule or the Fleming's left-hand rule states that if the left hand is held with the thumb, the first finger and the second fingers mutually at right angles, so that the first finger points in the direction of the magnetic field and the second finger in the direction of the current, then the thumb points in the direction of motion. Remember, in the Fleming's left hand rule, we strictly use the left hand. Remember, in the right hand grip rule, we were strictly using the right hand. But if you are dealing with the motors, the left hand rule, here we use the left hand. So this particular rule is saying that if the left hand is held with the thumb, that is, you hold your hand in such a way that the thumb is perpendicular to the first finger and also perpendicular to the second finger. You hold your hand in this particular manner, thumb pointing upwards, first finger in this direction, then the second finger, obviously in a normal situation, it will be pointing towards this particular direction. So you hold them perpendicular because if you try to estimate the angle between this particular, that is this particular, the thumb and the first finger and also the second finger, this angle should be 90. That is what we mean by perpendicular or mutually at right angles. Right angle, remember, means 90 degrees. So if the left hand is held with the thumb, the first finger and the second finger mutually at right angles, so that the first finger points in the direction of the magnetic field. So you take your first finger pointing in the direction of the magnetic field, then actually the second finger will point in the direction of the current. You take your second finger in the direction of the current, then the thumb will always point in the direction of motion. So if I apply this particular rule here, then if this is my north pole, then this is my south pole. Then another point you need to notice that whenever you are given a magnet, the north pole represents the origin of the magnetic field, then the south pole represents the end of the magnetic field. So magnetic field lines will always originate from the north pole and end at the south pole. So this is the direction of the magnetic field lines. So you take your first finger to point in the direction of the magnetic field lines, then you take your second finger to point in the direction of the current. If this is my current, remember this is an arrow indicating that the current is moving downwards. So you align your second finger in the direction of the current, then you realize that actually the thumb will be pointing upwards or in the direction of the motion. So an easier way of remembering this is that the first finger, we have F here, represent F and F. So as you can see, first finger fields represent the field. So you can take F and F to remember that always the first finger represents the field. Then the second finger, we have the current. We have C here, we also have C here. So C and C. So you just remember that because the second has C somewhere, then that would represent the current. So we have C and C here represent the current. Then of course the thumb, we have M here. Then this one is starting with motion. So M represents the motion. And the other thing to remember is that it must strictly be the left hand. It must be the left hand. Because if you apply the same with the right hand, you'll actually obtain opposite results. So you just align, you take your hand, then the first finger, you align it towards the direction of the field. So the field, we've said they move from the north pole towards the south pole. Then the second finger, you align it along the direction of the conductor, but towards the direction of the current. Then observe the direction of motion of the thumb. Where the thumb, because for my case the thumb is pointing upwards, then I expect this particular conductor to move upwards. The direction of the deflection of the conductor will be upwards. Then another point that I see students actually confusing is when to use the left hand rule, the Fleming's left hand rule, and when to use the Fleming's right hand rule. Now, remember this. The left hand rule, or also called the motor rule, is strictly used when we are dealing with electric motors, when we are using with electric motors. So remember, an electric motor will always convert electrical energy into mechanical energy. Remember, mechanical energy is categorized into potential energy and kinetic energy An example where an electric motor is applied is in the working of the fan. That is the fan that is used in houses or supermarkets or in shopping malls to reduce the temperature of the room, or to cool the room, or sometimes to increase also the temperature of the room. So those fans, they convert electrical energy into kinetic energy. So a material or a device that converts electrical energy into mechanical energy is what we are calling an electric motor. So when we are dealing with electric motors, we strictly use the Fleming's left-hand rule to predict the direction of motion of that particular conductor, or sometimes the field and even the current. But when you are using an electric generator, remember, an electric generator will always do the reverse of an electric motor. We've said that an electric motor will convert electrical energy into mechanical energy, and we've said mechanical energy, we can talk of kinetic and potential energy. So essentially we are saying that a motor will convert electrical energy into kinetic energy or into mechanical energy. But a generator, an electrical generator, will strictly convert now the mechanical energy into electrical energy. Please do not confuse between these two. I'm saying that an electric motor will convert electrical energy into kinetic energy. An example, we have given a fan. If you see a fan rotating, it will only rotate if you are connected it to electricity. And the electricity is what we are calling the electrical energy. So the fan, the motor within the fan, converts the electrical energy into kinetic energy, which is a mechanical energy. So whenever you are dealing with an electric motor, use Fleming's left-hand rule. But whenever you are using an electric generator, and you are saying that an electric generator will do the reverse of an electric motor, an electric generator converts mechanical energy into electrical energy. An example of mechanical energy is the kinetic energy. So for example, you are saying that an electrical generator can convert kinetic energy, that is energy in motion, into electrical energy. A good example of an electrical generator is the bicycle dynamo. The bicycle dynamo will only work if the wheel of the bicycle is actually rotating, because when the wheel of the bicycle rotates, it also rotates either the magnet or the contactor in between. Therefore, it converts the kinetic energy or the mechanical energy into electrical energy. For example, the electric motor can be used to, the electrical generator or the bicycle dynamo can be used to light maybe the bulb of that particular bicycle. So a device that converts mechanical energy or kinetic energy into electrical energy is called an electrical generator. And whenever you are dealing with an electrical generator, strictly use Fleming's right hand rule. Use Fleming's right hand rule. And we have given examples. So kindly don't confuse between the two. Electrical motor converts electrical energy into kinetic energy. Then if you are using an electrical motor, strictly use the Fleming's left hand rule. But an electrical generator converts kinetic energy or mechanical energy into electrical energy. Then if you are using an electrical generator, we strictly use the Fleming's right hand rule. So I think we've come to the end of our class today, but we need to discuss the quote of the day. The quote of the day stated that life is like riding a bicycle, such that for you to stay balanced, you must keep moving. Now, what does this particular quote mean? The quote is warning us against feeling complacent or contented with what we have already achieved in our lives. Rather, the quote is encouraging us to always stay hungry and motivated for the next opportunity that comes in our life. And always remember that whenever you attain a certain level in your life, there is always the next level, and that should be your motivation. And also, be careful not to waste your future opportunities for a temporary comfort. And lastly, never ever stop learning, because life never ever stops teaching. So that is the end of our class today. Now, dear my viewers, I know that it's been long since I posted a video, but you've always been supporting me, and I don't take that for granted. I've seen several comments of people wanting me to produce more videos, and because of your support, I've seen it important to continue producing more videos, and I promise to keep even producing very many videos and quality videos. But I'll also beg you to hit the subscription button and also to turn on the notification bell, so that whenever I upload a new video, you will actually be the first person to get a notification. Actually, I'm very happy and very excited to be back, and let's keep this going. We are here to change lives. We are here to help students. If there is a concept that maybe you've not understood well, just drop a comment in the comment section of this video, and I'm actually going to help where necessary. Thank you. Let's meet in our next class. This is Kind Tuition Academy.